thank the organizers for the invitation. It's very nice to be back here. I was asked to talk about LISA sources, so the electromagnetic counterpart for LISA. But it turns out, just by chance, that there's a talk today, a 1-hour talk later this afternoon, right after the conference, which was mentioned, and it's at 1 p.m., so sorry for the confusion. So it will start at 1 at the CFA in Phillips Auditorium. It will be a much more detailed talk on this subject. So I would like to save some time on this subject and talk a little bit also about some interesting ideas which were not discussed during the last few days about LIGO. But just to summarize and advertise Zoltan's talk, so the main question for LISA is what type of electromagnetic counterparts you expect for merging supermassive black hole binaries, which LISA will detect. And this is a very quickly growing field. There were several breakthroughs and different predictions were made which were quite different from one another. So originally, it was believed that there would be a gap which would be opened in the gas. So we're assuming that there's gas surrounding the supermassive black hole, the merging supermassive black hole binary. But it was assumed that if there's a gap, then there's no inflow across the gap, and it would be a relatively electromagnetically quiet region. But it turns out that this is not the case, and you do expect electromagnetic signals all the way to merger and after merger. So what LISA can do is localize the source and tell you exactly where when the source will happen, so even before merger. So even several months after a LISA observation, it will be capable of saying to second or 10-second accuracy when the merger will happen exactly. And it will localize the source on the sky to some accuracy just by measuring the gravitational wave signals. And you can see the rough scale for this is between 100 arc minutes down to 1 arc minute. So this depends on spins and other parameters. If you have spins, you can localize the source much more accurately. And this is as a function of look-back time, so time before merger. So you can see that even a year before merger, you will be within the LSST field of view. So you will be capable of looking for electromagnetic variability, which is presumably has the same time scale as the orbital frequency of the binary, which is related to the gravitational wave frequency. So just by measuring the gravitational wave frequency, you will have a chance to identify the source or look for the source on the sky within this area and look for a particular signature. The question is what exactly to look for. And there are lots of ideas what to look for as a function of look-back time before merger. So very early on, 100,000 years before the merger, when the binary is still in the pulsar timing array frequency band, you have periodic accretion and Doppler shifted mini-disks around the center here as the binary orbits. So you can look for variability in that case. In the LISA window, you can also look for some electromagnetic signals, which Zoltan will discuss. And after merger, there's also a possibility for electromagnetic signals coming from the gravitational wave interactions with the accretion disk, but this is expected to be faint. And you can have an effect, a mass loss. So gravitational waves carry away mass, and this leads to shocks in the disk, which can heat the disk and cause it to flare. And there can be a recoil kick, which also affects the disk. And you can have an accretion afterglow after the merger. So this is how the spectrum is expected to look like. So you expect to have a circumbinary disk with 2 mini-disks surrounding each individual object, which generates a little bit higher frequency signal. So this is an X-ray signature coming from the mini-disks. And there's the UV spectrum of the outer disk. And you expect electromagnetic variability in the X-rays. So this is the gravitational wave strain, which will be measured by LISA before merger, 7 days, and within the last day, approaching merger. And you expect to see X-ray variability with roughly the same period as the gravitational wave signal. So you should be looking for these types of events near merger. The other question is how the gas changes the gravitational wave signal itself. And we've written some papers about this subject in 2011. So it turns out if you have an extreme mass ratio in spiral, so a small object orbiting around a supermassive black hole, which can be a 10 solar mass black hole up to an intermediate mass black hole, then this object is affected by an accretion disk if there's an accretion disk surrounding the merger. And this changes a little bit the gravitational wave signal, which is detectable. So there are various effects we looked through and asked which of these would be most significant. And it turns out that the phase shift caused by these perturbations is significant. It's higher than a radian for different radii, depending on where you put the source. If you put the source far away, sufficiently far away from the central object, then compared to gravitational waves, the perturbations will be more significant. So here are the various effects. It turns out that just the gas-driven migration, so the spiral density waves induced by the object, is the largest effect which perturbs the gravitational effect of these waves, perturbs the orbit, the in-spiral rate the most. And this will have a phase shift of several tens of radians, which will be significant. And now back to some LIGO questions. So I think this is an important point which needs to be emphasized. So there were several excellent talks yesterday and on Monday on this subject. So the main question for LIGO is what is the astrophysical origin of the mergers that LIGO sees? And there are various channels which have been highlighted. I just want to make a simple point that there may be a question on the rates of mergers that LIGO sees. So this is the current estimate of the merger rate density in the universe of black holes. And the interesting thing is you can do a very simple estimate, which is an upper limit, approximate upper limit on the rates for sources in globular clusters and galactic nuclei. And this is that you assume that each black hole merges at most once in a Hubble time in a globular cluster. So let's say this is the case, because when they merge, they are usually kicked out from the cluster, so they cannot merge significantly higher number, significantly more than once. And it's very simple to count how many stars you have in globular clusters and estimate how many black holes you expect to see there. So you expect 0.3% of stars to turn into black holes. And this gives you, and you know how many globular clusters there are in the universe. And so this gives you an upper limit on the rates of 30 per gigaparsec cube per year for globular clusters and about the same for galactic nuclei. So even if all black holes merge. So I think this is an important thing to emphasize, that the rates, which are currently a little bit uncertain, between 40 and 200, are still higher, are already higher than this maximum limit, which is, I think, interesting. Of course, you can say that this is only for old clusters. Maybe young clusters add to this population, and so on. But still, we have to be careful if this will be measured to much higher accuracy in O3, and say it zooms in at 120 per gigaparsec cube per year, then it may be a problem. Okay, so there were some channels talked about already by Ilya, Selma, Fred, and Smadar yesterday. Just would like to highlight that there's this there's this possibility for galactic field triples to explain the LIGO sources. But in this case, so there are problems, there are questions with all of these possibilities. So for triples, the estimate made by Silsby and Tremaine and Antonini et al. Is that the rates are still at maximum at the order of 10 per gigaparsec cube per year. So it's a little bit under the current estimates. Similarly, for globular clusters and galactic nuclei, galactic film binaries can produce this rate, but the rates are extremely uncertain in that case because they are unknown processes. There was another possibility pointed out that dark matter halos may consist, at least in part, of black holes, primordial black holes, and this may explain the rate. However, this is an exotic possibility, and there's no current evidence for these objects. But just to say something about this possibility, so there were basically two ideas put forth. One is that you have primordial black holes which comprise 100% of the dark matter in the universe. And in that case, the rates work out to be correct, match the LIGO rates. But this has been already ruled out by the observation of a globular cluster in a dwarf galaxy, which would be disrupted by these objects. So you don't expect to see such globular clusters in the centers of dwarf galaxies if there's such a large population of these black holes. The other possibility is if you only have 0.1% of dark matter in primordial black holes, and let's say they are in binaries to begin with in the early universe. So this has been shown that this also produces exactly the same rates in this case, and you don't have any theoretical limitations in principle. But the question is, why do you expect such binaries in the first place? It turns out for 30 solar mass primordial black holes, they should form when the temperature of the universe is around 30 mega electron volts, which is nothing exceptional, so it's not clear why black holes should form at that time of this mass. But it's still a possibility. The question is, can we rule this possibility out using LIGO? And it may be possible using the mass distribution of objects. I think this is interesting. So there's an interesting question. If you measure the rates of mergers, how can you measure independently the unknown mass distribution of black holes and the relative probability of mergers for different black hole masses? So it may be possible that higher mass black holes merge more easily than lower mass black holes. So if you only measure one number, the merger rate per mass, you will not be able to independently constrain both of these unknowns. But the interesting thing is that you can, in fact, measure both masses independently. So you can measure the mass ratio and the total mass of the merger. And you can use this information to learn about both of these unknowns. And this is how you can do it. So this is in a paper that we have written recently. So all you need to do is take the logarithm of the measured merger rate and merger rate density and take this double derivative with respect to both masses, and you can easily show that in this case this drops out. So the mass function, the initial mass function of the black holes completely drops out from this formula if you are able to measure this quantity. And so you get direct information on the relative likelihood of mergers, which is different for different channels. And so we've estimated what it would be for different channels, and it turns out it's just a simple number in different cases. So for primordial black hole binaries, this turns out to be very close to 1. And this is different for objects formed by gravitational wave captures, so close encounters between objects forming binaries due to gravitational wave losses. would be 1.4. And if you have objects in galactic nuclei, you have a different number, and globular clusters would have different numbers. So in principle, if you have hundreds of sources or maybe 1,000 sources, you can start to constrain the merger channel just by measuring the mass distribution. For globular clusters in particular, this is what you expect. So there's a very interesting universal feature independent of the mass function. So you can ask, what is the relative likelihood of merger compared to the random pairing drawn from the underlying mass distribution for different mass functions? So here we have power law mass functions with exponents -1, -2, and -3, and we also have the Baczynski mass function predicted from population synthesis models. And we ask, what is the probability of merger for a fixed mass relative to the random pairing probability? And this turns out to be just simply proportional to the total mass to the 4th power for globular clusters. So this is quite interesting. And the reason, so you may wonder why this may be. Why is it more likely for higher mass objects to merge than lower mass objects in globular clusters? And the reason is that higher mass objects form binaries more easily. They can be exchange interactions, exchanging low mass objects, stars, into for high mass stars in binaries. And you can also have a core collapse or a mass segregation effect, which increases the likelihood of higher mass objects to merge. So this is one thing that you can look for to identify globular clusters as the origin of mergers, just based on the mass distribution. The other thing that you can look for, which was already mentioned, is these multiple generation of mergers. So you can have a merged remnant merge with another object within the cluster. And in this case, the merged remnant will be more massive than the original black holes. And it will merge with a normal black hole, typically, from the cluster, which would have a mass ratio of around 0.5. And so our estimates predicted that it would be something like a 7% among all mergers in globular clusters. Carl Rodriguez has similar papers, and Abbas Askar, more detailed papers on Monte Carlo simulations of globular clusters, which predict similar numbers. So it's around 10% or 15%, I think, in their case. So you can look for this type of effect and maybe isolate the globular cluster channel from the different channels. The other thing that you can do is look for eccentricity of the sources. And it turns out that for a particular source, so there's a possibility for this type of process, gravitational wave captures. So you can have single objects flying around in globular clusters or in galactic nuclei, black holes. And if they come sufficiently close that gravitational waves can carry away their initial kinetic energy, they form binaries that way, and then they merge. And in this case, the merger will be eccentric if the initial velocity dispersion is high, because you have to come very close for the binary to form in the first place. And you don't have time to circularize due to gravitational waves before the objects merge. And so there's a simple relationship between the eccentricity at the last stable orbit and the velocity dispersion of the environment. So if you measure the eccentricity to be the last stable orbit to be a few %, you can say that the velocity dispersion will be around 200 kilometers per second or something. So this will be, I think, a very good probe of the environment of the source if you can measure these sources in the future. And for globular clusters, obviously the velocity dispersion is lower, so the eccentricity will be expected to be lower. And you can also look for effects between eccentricity and the mass distribution. So it turns out in galactic nuclei that heavier objects sink to the center and are more densely populated. And so in that region, the velocity dispersion is higher, so they will be more eccentric. So the highest mass populations will be expected to be more eccentric, and the lower mass populations to be less eccentric. And these will be around the radius of influence in a galactic nucleus, and this would be near the supermassive black hole, within, say, 0.1 parsecs. And the interesting question is, how well can you measure eccentricity with LIGO, or the future versions of it? So with advanced LIGO, the network using LIGO, Virgo, and Cogra, we have estimated what is the eccentricity measurement error for a source at 1 gigaparsecs, and it's of order percent to 10 to the minus 3. So this is a quite low number. So you can, so LIGO will be, or this network will be very sensitive to eccentricity. So it may be able to find some of these sources. Okay, and here's another idea. So how else can you merge binaries? So suppose none of these, so something, you need an idea on top of what has been suggested. So this is a paper we have written with Hiromichi Tagawa, which was just accepted to PRL. So you have, so the idea is let's have a star which undergoes an explosion, or the envelope increases of the star for some reason. And so the envelope is ejected in a binary configuration. So if this happens, then you can expect gas effects to bring the stars closer together, even if originally the objects were not in the common envelope phase, so were not close enough to undergo the common envelope evolution. And so here's an SMBH simulation. We just put initial conditions similar to previous works. It's a slowly expanding homologous expansion of the envelope, and here's this is as a function of time. The binary is orbiting at a much slower rate, so it appears not to be moving in this case on these time scales. But there's a lot of material surrounding the binary, and there's fallback on both objects, both this object and the other object. And the question is if this could produce a merger. So here's how the simulation goes on longer time scales. So you can see that as the objects are orbiting, there's a gas cloud surrounding the two objects, and this makes dynamical friction on the two objects, which bring the objects closer and closer together. And if we wait some time, as more and more gas accumulates in this region, the dynamical friction effect is accelerated, and the objects in spiral due to dynamical friction. And so in the end, they stop at some radius where they run out of gas, basically, which is something like 0.1 AU. So basically, in this way, the binary can solve this final AU problem, how to come close together without the common envelope, the natural common envelope argument. Okay, and some mergers with electromagnetic counterparts. So there's this other option which was not highlighted before. This is a paper with Imre Bartos and Zoltán Hajman, that you can have binaries in AGN at the centers of galaxies, where some of the binaries will cross the accretion disk and will interact with the accretion disk. It turns out that they will settle into the accretion disk on very short timescales, 10 mega years, and then they will quickly merge due to dynamical friction in this environment. So this will be within 1 mega year typically, and there could be an electromagnetic counterpart in this case. So I think it's an interesting possibility, but the event rates are not enormous. So they for sure, all events cannot be explained by this process, but there may still be enough events that this may be identified for some of the mergers for advanced LIGO. And how else can we identify the source? So here's another idea. So let's say you have an ongoing merger for LIGO around another object, say a supermassive black hole. So if this object is orbiting around the supermassive black hole, the gravitational wave signal will be Doppler shifted. And you can use this information to measure or to detect the presence of a supermassive black hole in this near this ongoing merger. And this is how far the object can be, the perturbing object, and how massive it must be for this signal to be significant. So it turns out you have to be relatively close to 10 to the 12 centimeters or 10 to the 13 centimeters for relatively massive objects. So with LIGO, it's probably not possible to do this, but with LISA, you can do it. And so there was a paper by Inayoshi et al. So if you have an object orbiting around a supermassive black hole, then you have much more time to wait in the LISA band before it merges, and so you can make a much larger arc here, and so you can basically detect the presence of the supermassive black hole even if this object is at a separation of or orbital period of 10 years around the supermassive black hole. Okay, so I've run out of time, but another option is gravitational wave echoes. So some events can be close to the supermassive black hole, can be detected not only with the primary signal, but the lens signal may be detected. And intermediate mass black holes can also be detected, but I don't have time to discuss this. I will just stop here with the conclusions. Thanks.
Okay, questions? Smadar.
Bence, do you expect an electromagnetic signature from your fallback idea? So in the simulation that you presented, it seems like there's lots of gas moving around.
Yeah, that's a good question. So the problem is, you would think that there would be lots of gas and there could be an electromagnetic emission, but the problem is that this process takes the binary only down to something like 0.1 AU. And from that point, you need gravitational waves to merge the binary, and it takes millions of years to do that. And so the gas may be gone by that time, who knows. But it's a good point, and we should investigate this.
So I actually wanted to make straight up argue with your upper limit on the rates from globular clusters. Okay. So I did the similar back of the envelope thing to what you just said, and actually came up with exactly the same answer, which was kind of cool. But the assumption that went into that was that we're looking at the present day populations and spatial density of globular clusters in the universe. And as you know, there's pretty significant evidence that roughly 90% of globular clusters have disrupted by the present day. So if you take the upper limit on, if you take some of the upper limit on the co-moving density of globular clusters and you assume that 90% of them disrupted, I think that number, well, I just did it, the number comes up to about 1,000 per gigaparsec cube per year as an upper limit, which I think is really just more evidence for Fred's claim that rates are kind of a fool's errand because you can just keep tweaking with cosmology until you get what you want. But
yeah,
that's just
yeah, that's a good point. So in the past, there could have been much more globular clusters than we see now, and maybe that's the reason why you can push this number up. But you really have to push this number up by an order of magnitude, maybe. And yeah. So. But I thought so. Your original numbers between 5 and 15 in your paper, gigaparsec cube per year, that took this into account, right?
No, that was based entirely on the present day observed globular cluster mass function. I haven't found yet a clever way to wrap in sort of any cosmological evolution because it's extremely hard.
Okay, something to discuss over coffee. All right, let's thank Bence again.